Yeah, it is. So if you wanted to figure out where they leave the ice, and so far, just to bring everybody to the same place, the person started here and slid this circular path. Eventually, they're going to be going so fast that they're no longer going to stay on the ice and they're going to become a projectile. We're trying to figure out where that happens. We spent part of yesterday coming up with a relationship that helps us put together how fast they are going depending on the angle. If you look at what this is, r is a constant, that's the radius. It's going to be the same number all the time. G is a constant, it's acceleration of gravity. This is a relationship between how fast they go and their angle that they make with the vertical. It looks to me like since cosine starts at 0 degrees, their velocity in the beginning is 1 minus 1, which is their velocity starts at 0. Of course it does. They have all gravitational potential energy, and then they begin to slide. So as theta increases, this is going to show that the velocity increases. Where at the very end, the velocity is going to be exactly what we expect, which is the square root of 2gh, right as they hit the ground. Because that's going to be when cosine is 90 degrees. Cosine of 90 degrees is 0. 1 minus 0 is 1. So I get v equals square root of 2gr. Those aren't a surprise. This is just the relationship. So now I know, based on where the angle is, how fast they're going. That was the first part of our solution. The next part now is to figure out whether you can stay on the ice at that speed. That's the speed you're going to have, period. Whether you're on the ice or not, that's just the speed you're going to have. Now, what we want to know is, can they actually stay on the ice? Now, to know that, we know that we have a condition that must be met. There must be an unbalanced force towards the center that is equivalent to the amount of acceleration required to stay in a circular path. Now, when I look at this, I recognize that there's actually two accelerations. There's an acceleration this way. That's got to be the acceleration that's causing centripetal motion. There's also an acceleration this way. That's what's speeding that little guy up, making him go faster. So I don't care about the one making him go faster. I've gotten a statement of his velocity in terms of the angle, but I do want to consider what's happening in the y direction. There are two forces acting in the y direction, I think, and I think it's those two forces that will determine whether they stay on the ice or not. I bet one of them is getting smaller as they go faster and will approach a limit. So what forces are acting in the y direction? I'm seeing that there's going to be an mg cosine theta acting. Just like an incline, it's the amount of the force that's towards the center. But this would be the one that's into the ramp. I'm making that positive. Towards the center of the circle has to be positive. And there's probably a normal force pushing away from the circle. Why? It's a surface. Normal forces can only push away. Well, it seems to me that there's some limiting factor here. And I will have yet another relationship between theta and velocity. Seems to me I need to eliminate velocity so I can solve for theta. Now that was 4 minutes and about 27 seconds. So I've taken some of your time. I'll give you back 2 minutes. So that's all that's left to do with what's written right here, right now. So 2 minutes.
No, R is going to cancel out.
Let him do it. He can do it. He's a smart guy. Just do the math. No. All right, what you guys at home are missing is currently Matt is having an existential crisis. Max is having an existential crisis. He is unable to get an angle. And he knows he's made a mistake, but he's having difficulty finding it, and it's leading to us laughing at him. That's not a good thing. We shouldn't laugh at our friends. But I'm not any of your friends, so it's okay. So Lauren, how you doing over there? All right. How many of you are stuck with the normal force? I can say this. You guys are stuck with the normal force? That's good, because that person is still on the ice if they're experiencing a normal force. That's my hint. It is a good hint. The kid's safe. They're right there on the ice. They're not in trouble. They're not airborne yet. But there could become a time when they're no longer on the ice and they won't be feeling any normal force. That's going to be bad times for the kid.
He's just like sliding down. It's like, where's the ground? I want to do that. But instead of snow, it's obviously not the.
Subtracted 2 over the other side.
Come on, folks. We got more to do besides this one. This one's just for fun. And it's your last homework assignment. Why is Kyle standing up?
He doesn't know how to do it.
No, you were fake hitting Dylan. That's different. I'm sorry, you lost the privilege to talk back to me when you did the fake hit.
You can't say anything.
Excellent.
Where's the fun?
I didn't know that, but okay. That will make a difference. Because he was doing this. All right, folks. I've had all the fun I can have waiting for you guys, which means I've had no fun at all. So at this point, if you're having difficulty, you're really, really going to need to do some work. They leave the ice and the normal force goes to 0. That makes this RG cos theta equals V squared. So you've got this relationship and you've got this relationship. Eliminate V. When you eliminate V, all of the other variables fall away as well. Which means you can get a solution for theta, where theta equals 48 degrees. An actual physical limit to this problem. Interestingly enough, it's true for every single size sphere there is. Whether this is, a diameter of 100 meters or 2 meters. You build these for kids to play on. 2 to 3 meters is about the right size you tend to see. And of course, if they're actually being built for kids to play on, they tend to bring this up so that's closer to that 48 degree mark. So they come off the slide just as they're reaching the ground. They don't actually allow them to plummet to their, demise. Now, of course, the other side of that is where you would ever position an ice sphere probably would be a place where this is filled with snow. And they would probably, fall into 18 inches of lightly packed snow. They'd probably be okay. Probably. Now, I don't know if you guys know this, but they had one of these at Glencliff Park for years. Back when you guys were little. Really? You threw something? Are you 12? Don't throw stuff in my classroom. I need a new job. I can't take it. I just can't take it. People throwing stuff. Anyways, Glencliff Park had one of these. They replaced it shortly after I moved here, but I had little kids there. It wasn't a full circle. It didn't look like a sphere. It was a curved slide. A curved slide would be the same thing if it's rounded, and it would do the same thing. You would still fly off of it. It's Florida, though, so it was probably muddy over here, so that was okay, too. But, you know, if you actually looked at one of these and look at the speeds you attain, it's not pleasant. I mean, they're moving when they leave it, and they are moving when they hit the ground. It could be dangerous for children, but it's for children, so we're okay. They're pretty young. You can always start over, you know, that kind of stuff. So that kind of thing. Those are funny jokes. All right, so I got to be honest. We're really just beating this conservation of energy thing, but it's because you guys have trouble with it, clearly. So we're going to look at another conservation of energy problem. And for you guys at home, this is going to require that you guys go on a bit of a field trip, okay? It's going to make you sick, I know. So I'm going to go ahead and set this up so you can go on your field trip. It's going to involve me first turning off the chroma so that, you know, you don't see the background anymore. And we're going to move you over to the station where I have something set up. I don't know how much battery life I have left, so all right, so I think you can see most of it. All right, so I've got a pendulum bob here, and I've got this kind of apparatus set up, clamped down. I have a diverter beam here that I can change where I place it. You guys at home see this okay? Give me a big yes if you can.
Yes.
There it is. That wasn't a very big yes, but at least somebody's paying attention. So I can put energy in the system by lifting this up to the side. If I lift it up perfectly sideways, I think that the length of the string could probably help us figure out how much potential energy there is. And then I can release it. When I do, it's going to acquire some velocity. When it makes it down here to the diverter, it's going to suddenly change the radius of the system, and the system may or may not be able to travel in circular motion. I say may or may not because it doesn't always. There are places where I can place the pin where it will travel in circular motion for sure, like right now. Clearly circular motion. You guys saw that okay? The fact that it moved a little bit, that unfortunately took out some energy, so let me try and clamp that down a little more. And I'm going to turn it a little bit this way so that the angle allows people at home to kind of witness it too. So let's actually clamp it down a little bit. Down, sideways. I think it was in circular motion an awful lot, don't you? So let's undo that. And I know that if I put it too close, there's no chance for circular motion, right? And right here, it shouldn't even make it back up to the top. If it does, it won't be going very fast. You need to see this because this is going to be a circular motion fail, right? It's going to have a velocity that approaches zero as it gets closer to the top. We know it has to have a velocity to stay in circular motion. It doesn't even make it part way up. This is to hopefully help get the idea across to you guys that even though it might have the energy to get back up there, since it can't maintain circular motion, it can't maintain that motion. It has to be able to satisfy both things. That suggests, though, that there's a place here where I can put this, where there's a threshold. A threshold where it will just barely complete circular motion. I don't think that was it. If you watch closely, it fell well below the circular path. The question is, well, where do I place this? What fraction of the length is the threshold where I will get circular motion? And I'm not asking that in maybe an arbitrary way. I'm saying I would like D, this distance, as a fraction of L, this distance. And we should be able to prove whether you're right or wrong. I'd say 10 minutes should be enough. bet you can do it in 5. Let's go with 10 minutes. So I want D as a fraction of L. Now, just because I don't want you guys to get too sick as I move you around a little bit. How about we draw ourselves a little picture? Pictures always help, maybe. So, I think in our little picture, we'll have the attachment point here, the diverter beam there. I'm going to put a string, something like this, starting nice and sideways with my weight right here. I'm going to call this L and this D, and if you need it, that's M. Should make it to here. There we go. Is that enough pictures to help you? I hope so. I hope so. All right. I'll pick on somebody here in a minute.
Mr. Shaw.
I think we can see that there's a clear system in which the energy that's put into the system at the beginning stays within the system since there's nothing to take the energy away. And I, just from looking at it, recognize that when I'm up here, I probably have one kind of energy if I'm not moving. And then when the system makes it back to, say, this point, depending on what you have chosen for your lowest point or your reference level, you either say that it has just kinetic energy here, or you say it's got kinetic and potential. So it doesn't matter which way you do it, you're going to get the same answer. But this just tells us how fast it's going. That's all that conservation of energy can tell us anyways. So that's the start, that we're going to have something about conservation of energy, with the goal being to figure out how fast it's going at this location. Did you do that yet? Because if you haven't done that, you can't go any further. And I know that some of you, you're just as tired of doing this as I am, but I have some students who can't do this. So I'm really going to lean on them because I know who they are. They're the ones who are desperately writing right now. So let me give them a second, then I'm going to lean into them some, and they're going to be unhappy about it. But I don't really care. Lauren, go ahead.
I get how to find the velocity at the very bottom of it, but then when it comes to doing the second height, like I don't know what to put for H.
Okay.
That's where I just get confused. I know that happens.
Yeah, I don't really need this velocity here,
I know.
but okay. I agree that it's probably difficult to figure out what that height is if you're not sure where to go with it. Would you agree that this height is 2 times the radius?
Yeah.
Okay. So if I wanted to figure out the radius, I'm just going to draw something here and see if you can figure out the radius from what I add here, okay? This length from here to here is L. And this must be the radius. Can you figure out the radius in terms of L and D now?
L minus 1.
L minus R would give you D, sure.
So
So if I want R instead,
L minus 3.
sure. So that would suggest that the height to which it rises is 2 times L minus D. Yeah, you're going to have to make that. So I should wait just a few moments and then hit somebody up to tell me with what they set up when it comes to conservation of energy. I'm pretty confident I know who I want to pick on. I've got about 4 people I think who should probably speak to the class because, you know, I'm desperate to hear what they have to say. Minute left. It's a long minute. Mostly because I'm being all quiet and I can't stand being quiet. Amanda, I know you got knocked out of the whole thing. Now you're back. Do you think you could talk to us about the conservation of energy part here?
I have it for the first, like when it's at L. Does that work?
Yeah, what kind of energy do you think it has when it's here?
I put gravitational.
What's that?
Gravitational?
Okay, and how would I write that?
I put MGL.
Perfect. So now we want to talk about here. What kind of energy do you think it has when it is here?
Potential and kinetic.
Okay. So the kinetic, I think, is pretty easy. I'll take care of that one for you. 1/2 mv squared. But you have to tell me what the potential is there.
MG L cosine theta.
No. I think a lot of people have worked in an angle because they were looking at the last problem, but just like we were talking about a moment ago with Lauren, this is representing the height above the reference level, which is this height. Because that's where it is right there. So instead of using any angle, because there's no angle here to worry about, I think we'd rather put in 2 times L minus D. Set that aside. This is the velocity in terms of L's and D's and stuff. Yeah, you could get rid of M, but this is a circular motion problem. I think the circular part is necessary here. So I spent a few minutes, going through the energy. Now let's talk about the circular part. And I think I want to hit somebody else for the circular part. So how many forces are acting on the object when it's right there? Can you name a force? All right, you got the easy one. Jaden, what's another force that's acting on it when it's right here? Okay, how would I draw the tension? What direction would that arrow be? If the cable's here, can it pull upwards? Yeah. So tension's going to be downwards. There we go. Those are the only 2 forces acting on it, the only 2 things connected to it. And in this case, I think it's even a little easier than the last problem because it's all one-dimensional. The tension and the weight are in the same direction. So Jane, what do those have to equal? There we go. But there is no R. What do I put instead of R? Not 2L minus D. Just L minus D. It's just the radius. L minus D. There we go. All right. The limiting factor now. Where's the limiting factor? Ryan, what's the limiting factor? That's right. Our limiting factor is when the tension equals 0. That's our limit. That's it. Put it together. There's not much to do now. I would probably say something like mv squared equals mg times L minus D. Yeah. Get in there and mix it up with those numbers. Because I want D equals. I bet that M goes away. I bet the G goes away. I bet all that's left are some D's and L's and maybe a 2 and a couple of negative signs. Maybe a 1/2. All right, I'll pick on one of you. You got 60 seconds to work out your algebra. 60 seconds. 55 seconds. We know it's going to be less than L. If you get something more than L, you've probably made a mistake. And we know it's not half of L. We tried it, didn't work. In fact, we know it's got to be bigger than half of L. We're on our last 30 seconds. No stress. I'm calling on you, Lauren.
Actually, do.
Hurry.
Okay, well, no, now,
No pressure.
stress.
Am I calling Justin? I haven't called on him yet. Calling Xavier. I'm not calling on Kyle. Maybe Damien. Of course, I could call on Annika too. Joey. I like it when they're at home and they just barely hear their name and they just like pop up. Like, I like that. All right, that's been enough time. So we're going to hear from a lot of folks. We're going to see how many people have the same answer and how many people have different answers, considering all they have to do is algebra. So let's start with Lauren. What'd you get?
Wait, calling you next.
Oh, wait. Calling you next? This is next. Joey, what'd you get?
3/5.
3/5. James, what'd you get?
2/3.
2/3. Damien, what'd you get? 3/5 again. Great. Davon, what'd you get? 3/5. All right. Kelly, what'd you get?
I screwed up. That's what I got.
What number that is, but okay, I'm writing it down. Let's put it as a fraction though, so I screwed over up. There. And I don't know, Justin, what'd you get?
2/3.
2/3. Well, I thought we were gonna break this tie, but it doesn't look like it yet. Lauren, are you done yet?
Yeah, I got it, ready?
Yeah.
3/5 of L.
3/5. Great. All this can be times out. The right answer is 3/5, by the way. It is 3/5 all the way. So you guys got 2/3. Check your math. I bet it's a sign problem. I bet you forgot to distribute the negative sign. So that means we should test this out. Right? We should know right away. We should walk over right to that thing and test it out. Let's do it. Let's test it out. Because I think that's too easy for us not to figure out and see if it's true. So take this over there. Give it a shot. All right, so the whole string is 55 to the center of mass, 54. So I'm going to go with 31. Down about 2 centimeters. All right, between 31 and 32, this should do it. It should stay in circular motion, but just barely. I'd say we're right at the threshold there, wouldn't you? Yeah. That's some good mathematics. All right. Way to go. Now, if you couldn't do that, you're going to fail whatever quiz I feel like giving you. So I'm gonna put it out there at this point. And look, I'd say I've been pretty patient here. I think you guys would have to agree with me. You're going to have to step the games up now. Okay? This is what you have to do. This was on the exam a couple years ago, actually. Now these problems, again, barely what it is we're supposed to be doing. This just barely scratches the surface because we're going to have rotational motion. Now we have to add into this angular momentum, moment of inertia. All that stuff's got to be a part of this. So when I say we're scratching the surface, I want to be very clear. We've done the same problem now more than once. We're going on 3 times, right? Circular motion, setting the limit to this one area, making sure one of the forces goes away, setting the energy equal to some other thing. They're not all going to be like this. I'm kind of beating this one apart because I need to make sure you guys are seeing the parts of the problem that are energy parts and the parts of the problem that aren't. But you understand that we got to get away from this. So I feel like this is it. We've done the part that we have to do here. And we're going to have to move on from this. All right. So you guys, you have practice, do your homework. There's lots of practice in there. Get those pieces done. And how many minutes do I have left? 1 minute. Well, that bothers me tremendously. It means I gave you way too much time. But we're moving away from conservation of energy tomorrow. All right, this is it. You guys have conservation of energy homework. Do it. Practice. But I'm thinking Thursday, first 10 minutes of class for real. That gives you time to get your questions answered and come to tutoring. And then I'm thinking next week, Wednesday, we're going to have a test over momentum and energy because we're starting momentum full speed tomorrow. All right. Any questions about that? All right. Then I guess I'll have to make that really the bell rings now? I don't hear it. I guess that's the bell. All right, folks. It's been real. Can't say it's been fun, but it's been real. So see you all later. Have a nice day. You guys at home have any questions for me? All righty. It's been great, you know.